Okay, we are going to start the lecture today by taking a look at some problems from section 1.1. The last four problems are so-called parametric equations. So we are going to take a look at okay, in daily life you come across all sorts of instruments that act like a machine, but you still have some input into that machine, like a radio or a drill or something. The machinery does something, but you control some aspect of it. Like on a radio, you can change the channel by turning a knob. That element of the system that is at your disposal to change, sometimes in mathematics referred to as a parameter. That machinery is going on, but you can change something about that machinery. In problems like 29, you see x and y that are representative of ordinary variables, but there is also a k. The implication is that you can adjust the k until you get perhaps something that you want. Let me write down the equation. It says 2x plus 3y is equal to 4, and then I have kx plus 6y is equal to 8. So this is problem 29. The question is asking you for which values of the constant k. So let me write that, for which values of the constant k does the system have one of the three scenarios we said all linear systems might face. Either they have no solutions, or there is a unique solution, or sometimes called exactly one solution, or infinitely many solutions. We can characterize this by number of solutions being just 0 or 1 or infinity. We said every linear system suffers one of these three fates. There is no situation where they will have just 2 solutions or 3 solutions, so no such discussion comes about. Okay, these are 2 by 2 systems, and again, as I mentioned, this k is a parameter here. You could replace it by some number, and different numbers will create different scenarios. What you want to do is to give association between what k's will lead to any one of these different situations. Now, one way to handle this right now is by appealing to things we have seen in, say, college algebra courses or graphical representations of equations, and get our answers from there. Like if I go ahead and graph these two, then I can say which one of these 3 cases are going to happen. You remember in our previous lecture we said in a 2 by 2 case, either it can be that you have 2 equations that when you graph them, perhaps they look like 2 lines that intersect. And what does this point of intersection refer to? The point of intersection is the solution that you're after. That's the typical case. But then we said every now and then we come across some exceptional situation. What were the exceptional situations? This red and green could be what? They could be parallel to each other. So in this situation, we say, well, this one was one solution. Okay, and what is that case? Yeah, no solution or 0 solution or no solution. And then we had the other case, which was what? Where does the green go? Right on top of this thing is going to be the green. Now, how many solutions you have right now? So infinitely many solutions. Okay, right now our aim seems to be like this, but toward the end of the semester, actually, we are going to tend to pay a lot more attention to situations that are reminiscent of this case. We want to design our system so that things will happen that will be similar to this. So the question is actually important, and right now we are just getting our feedback. Now, when we approach the problem from this visual perspective, we can just use the ideas we have learned back in college algebra. For example, very first equation, graphing of that, what would you do to graph that anyway? One of the approaches would be to put it in that slope intercept format or something like that, perhaps. So what would you do here? Say 3y is equal to minus 2x plus 4. To just make it look like equation that you are used to, what do I do now? Divide by 3. So if I were to graph this equation, what do I know about it? That it has, what kind of slope does it have? It has a negative 2/3 slope. And what's the y-intercept of it? 4/3. So 4/3 will be somewhere here. That's where we start. And then this means that for every 3 steps to the right, I have to take 2 steps down. So if I go, say, 1, 2, 3 steps to the right, this minus 2/3 means, a little bit of a problem here, but anyway, so I have the graph of y is equal to minus 2/3 of x plus 4/3. Now I go ahead, do the same thing to the other one. If I can, I say, well, how about the second equation? The second equation, I'll have 6y is equal to minus kx plus 8. And if I divide, what do I divide by now? Divide by 6. And I have 8, 6, which I can look carefully and realize that is same as 4/3. So this second equation, we notice that it has same y-intercept. So that is already a solution of the equation. That is, when x is equal to 0, y is going to be 4/3, and they share that point. So would that situation be possible? Like depending on what k is, I'm going to have different slopes. So the red line could be any one of many different kind of lines I might have here, depending on what k I got. But would it ever be a situation that will represent that case? Is it ever possible for this system not to have a solution? Now, we already see a solution here. For all cases, it's possible for you to take x equal to 0, so it is perfectly okay to take x equal to 0 and y is equal to 4/3. That is always a solution. So the fight is between this case and that case. That is ruled out. There is never a situation in this system that you wouldn't have a solution. So by now we say this system, our conclusion is this system always has x equal to 0, y equal to 4/3 as a solution. So it either has a unique solution, meaning that is the only solution it has, or infinitely many. What this problem is really asking you to specify the values of k that leads to that case and values of k that leads to that case. So what should k be? That you have definitely exactly one unique solution and no more. What should k be? So we notice that, like if I had taken k to be, say, minus if I taken k to be, say, 6, this would have been a line descending at slope -1 going down. So for example, for k equal to 6, I would have had that one. If I had k equal to 0, I would have gone straight. If I had k equal to -6, I would have gone up at slope 1. The only case that stands out is for what value of k? 4. The value of k, if k is 4, the slope becomes 4, 6, which is same as 2/3, which becomes same as that slope. It means that the red and green are going to have what kind of relationship? They are going to be right on top of each other. So in this case, what is k? You said 4. We could have guessed right off the bat. These numbers were friendly. We could have kind of seen what's going on. This is 2, 3, 4. This is 6, 8. This 6, 8 are just double of that 3, 4. If this is also a double of that, then obviously the second equation is just a copy of the first equation. That first equation by itself has infinitely many solutions. So it's kind of obvious from the start that k equal to 4 is special. If k is equal to 4, this is same as that, so you have infinitely many solutions. If k is different from 4, then you have a unique solution, which is always that number. So here we come, and final answer is the following. So tell me what to write for unique solution. What do you say about k? K not equal to 4. This k, infinitely many solutions, k is equal to 4. When it is a unique solution, what is the solution? Well, that is the solution. When it has infinitely many solutions, what are the solutions? Well, the solutions of that equation or that line will be your solution. Okay, so we see that in a 2x2 systems, we have an easy way of telling the cases where we can separate this situation from that. If these coefficients are proportional, what does that mean? If the ratio of these two numbers is same as ratio of these two numbers, it means that the graph of the two lines will be what category? Okay, either infinite or what? Or parallel to each. Either the two lines are going to be coinciding on top of each other, or they are going to be parallel and not touching each other. If the ratios are the same, it means the slopes are the same. If two lines have the same slope, either they are the same line or they're just staying apart from each other. These are the two cases it can be. Okay, so when does that happen? In both of these cases, the slopes are the same. Slope of red is equal to slope of the green. Okay, in both these cases, the slopes of the lines are the same. So how do you distinguish this from that? Well, how do you calculate the slope? Slope is a ratio of this to that one, ratio of this to that one. If they are the same, the slopes are the same. Another way of seeing the same thing is that these coefficients are proportional. If they are proportional, the lines are parallel to each other, then you can follow with the rest of the discussion. It depends what else you got in the problem. So this is problem 29. If you want me to do another one of these things, let me know which one it is, and I'll just is this clear what I mentioned? Okay. Okay, any other question from this bunch, or do you want to try it again? And if you have a question, bring it up on Friday class, and we'll talk about it. Use the idea of a slope and y-intercept or similar concepts, and you'll be able to solve it. So we are going to go to section 1, 2, and we are going to talk about the topic here is Gaussian elimination. we are going to take a look at this thing again in more detail than we did last time. Okay, we are going to be living with this idea throughout the whole semester. Okay, we have to learn it very well and know all the details of it to be able to handle all sorts of ideas in this class. Okay, we looked at some equation last time. We saw that if they are in a triangular form, then that's our lucky day. Everything will be great. What was the idea of a triangular equation? In the matrix format of it, there was a particular look to the numbers. I have some numbers here. I don't mention specifically what number. I just put some symbol here. And what was below this diagonal? We were supposed to have zeros below the diagonal. So we insisted in the triangular form that we'll have a situation like this. Now, particular numbers themselves are not important for me in this section for now. We are just talking about the look of the matrix. Okay, every now and then things don't line up exactly like this, and we want to broaden our definition and talk about things not just triangular but other formats. So what we are going to talk about is the echelon form of a matrix. To explain that, we need to talk about several other concepts. One is the concept of leading zeros. And the next is the concept of pivot. Well, what are leading zeros? By leading zeros, we simply mean the zeros that appear on a row of a matrix before you hit a non-zero entry. Okay, so these are leading zeros. So the zeros on a row that show up before a non-zero entry shows up, that's called the leading zero. Zeros on a row that are located before a non-zero entry. Okay, well, if these are important, then whoever is a non-zero entry, that guy is going to be important too. If this is non-zero, if that happens to be non-zero, we are going to refer to it as a pivot. So if that is non-zero, we are going to refer to it as the pivot. So pivot is first non-zero entry of a row. So let's just write down a matrix, for example, say 0, 0, 2, 5, 9, 0, 1, 7, 8, 11, 0, 0, 0, 0, say 6. So what is the situation here? I have, these are leading zeros of these rows. Then I have my pivot to be those entries. Now, you remember in the Gaussian, in the triangular form, we were insisting on cleaning entries below a pivot. By using that pivot, we were getting rid of every entry below it, and hopefully we're creating this particular look. Generalized form of that is going to be referred to as an echelon form. So let me go ahead and explain what's the echelon form. It's just like what you have seen with the geese and such flying. The idea, let me first draw something and then I'll explain the definition itself. If you have a matrix where number of zeros, the leading zeros from row to row increases. So as I go down, I expect to see more leading zeros all the way until perhaps the entire row being 0 elements. If I come across such a thing, I say I have arrived at an echelon form. So again, in echelon form, let me just write down a pivot. Suppose here's a pivot element. Here's a pivot element. That's the first non-zero entry of that row. And this one, well, it doesn't have a pivot element. What is showing up after the pivot, we don't really care what happens after that. So I might call it stuff. Whatever stuff shows up here, well, it could be 0, it could be non-zero, I don't care one way or another. So the matrix is divided into 3 groups. The elements of a row, they have their own leading zeros. Then you have your pivot element, and then after that is whatever else that is left. These guys may be 0, maybe non-zero. So long as you achieve a format that from row to row, the number of zeros increase until they can't increase anymore. Perhaps the last row could be just entirely zeros. That's fine. If I have another row after that, it's okay for the number of zeros not to increase because it can't increase anymore. Okay? So if you have entire rows of zeros, they'll be forced to be settled down to the bottom of that tank of numbers. They have to show up at the very bottom. Up here, they have to increase. So to give some official definition, there is one definition in the book. You might want to read that. I have a slightly different definitions. Either of them would be fine. If you happen to have a matrix with just one row, there is no dispute about it. It's an echelon form already. A matrix with just one row is already in echelon form. You don't need to do anything to it. Whatever it is, it's already echelon. And it's not a very interesting situation anyway. 2. If a matrix has 2 or more rows and row B is below row A, like I'm looking at 2 of these rows, say here is, well, let me draw another okay, let me just call them by something. Here's a row A, here's a row B, say. If I have 2 rows and row B happens to be below row A, then either row B has more leading zeros than row A, or row B is entirely 0. Okay, So I'm sure the very first definition is clear enough, but if you want to argue about the situation, here is one official sounding definition for it. Now, some examples are in order to help us see the situation. Tell me which one of these things is echelon and which one isn't. This one, is this echelon? No. This is not echelon, because, well, this guy got 2 leading zeros, this guy 1. That's not Gaussian. How about here? This is, yes, it's echelon, a matrix entirely made out of zeros. That's fine. We said that if you got all zeros, they have to be at the bottom of a matrix. Other than that, it's fine. How about this one? Yes, that's fine. It's because here I got 1. Here I got 3 of them. So long as I increase, that's fine. What's the difference between this and what we were doing last time? And last time, matrices were kind of ordinary shape where the number of zeros was going up 1 notch at a time. But now we are saying it can actually jump. That's fine. And that's going to lead to some interesting situations. So that's the definition of a echelon. Now we are going to take some matrices and try to solve it, the corresponding equation, while insisting on this echelon form of the equation. So let me go through some of these. Some of them are going to be straightforward, so I'm going to do it quickly, and some others I'm going to spend a little bit more time on it. So here's a question. Suppose the augmented matrix of a system is given. What we want to do is to find the solution. The problems that we are going to look at first are easy ones. Easy ones means that somebody has already done the hard work of reducing it to the echelon form. Essentially, much of the Gaussian elimination has been already done. All that is left for you to do is to do the back substitution and clean it up. Very first example is the following. So is a augmented matrix, means the variables have been taken out, and for that reason the book says, well, assume the name of variables are just say x, y, z. In that case, what is the straightforward method of solving it? What did we say we do? We do the back substitution, meaning this last equation really is a reflection of 5z is equal to minus 10, from which you figure out that z is equal to minus 2. You take it, put it in the back previous equation, work your way back up, and then you find what solution you might have. So in that case, you are already done. So I leave this thing to you to do, to find out. So all that we have to do is the ordinary back substitution that we learned last time. The question is, well, what if I didn't have this perfect triangular form? That is, my echelon formation was a kind of strange formation like one of these. The number of zeros were jumping around, and that leads to some interesting situation of its own right. So let's go ahead and spend more attention on those. For example, here is a matrix 3, minus 2, 1, 3, 1, 14. Yeah, I jumped 2 steps to the right. I mean, the equation is just like that. 2, 5, minus 3, 2, in this one I jump 4. There are 4 leading zeros until I hit my pivot -3, -6, and the last row is just all zeros. Remember, these are augmented matrices, meaning on this side we have our variables, on this side we have the right hand side. I could have called them say x, y, z, u, v, whatever you like to call them, x, y, z, say u, v, or more commonly they use index variables to deal with them. Okay, what does this last row of this matrix really mean? It just means somebody wasted ink there. It's like, okay, this is saying 0 is equal to 0. He didn't say anything. It's a useless row of a matrix. Some equation looked like it was there, and during the act of elimination it just got entirely eliminated and nothing is left of it. So if you have entire row of zeros with a 0 on the right hand side, if you put it there or you just exclude it, it doesn't make any difference. Nothing is going to happen by having it there or not having it there. So in order to make your writing shorter, you can just ignore it totally. Okay, past that we have to go identify our pivots. Who are our pivots? First of all, we notice, is this an echelon form anyway, before we go any forward? Yes, it is echelon form. So we are lucky. Somebody already has done the hard job. This is echelon form. These are increasing in the appearances. So next issue is that, well, who are the pivots? Pivots are these ones. Now we are going to have a bit of a terminology. The variables that are associated with the pivots, we are going to call them dependent variables or leading variables. So I'm going to have so in this case, who are the leading variables? This is, if I had written it as a full equation, who would have been the coefficient, who would have been the variable that's multiplying 3? It's x, is that right? If I write this all out in a traditional notation, it's going to read 2z plus 5u minus 3v. And who is pivot there? 2 is the pivot. xz or x3 is going to be called leading variable connected to that one, and so on. So in this case, these are going to be x. Who else? Who is the next? Z. And who's the next? V. Is that right? Okay. How about the rest of them? The rest of them, we are going to call them independent variables, or we are going to call them free variables. Sometimes we are going to call them parameters. In this case, are the remaining so who's left? Y and U. Now, to see what we are going to do next, it's a little bit more instructive if I write x, y, z, u, v and rearrange this matrix. What we are going to do is that the terms that include the the terms that include the free variables are going to be moved to the right side of equation. The terms with free variables will be moved to right. But before we get there, well, there's a problem. We got 3 equations really. We have 5 variables. We cannot nail down 5 things out of 3 pieces of information. So some of them have to play a free role. The other one are going to lead, are going to follow the lead of these 3 variables. So we are going to take this equation and rewrite it. So I'm going to pick this one. This is going to convert it to 3x. What am I going to write next? The next dependent variable is z. I'm going to write that. It's 1z. The next one is 1v. On the right hand side I had 14. I'm going to carry this minus 2y to the right hand side. So what is it going to appear as? Plus 2y. Is that right? And what's going to happen? What's going to happen to the to u? This 3 here meant that in my equation I had a plus 3u here. If I move it to the other side, what is it going to look like? Minus 3u. Okay, now somebody tell me what would the second equation read like after we apply this idea to it? 2z, and then what else? Hold it. All the dependent variables have to stay. So these guys stay. So I'll have 2z, what else? Minus 3v is equal to minus 5u. And the last one, somebody read the last one to me. Well, there isn't anything to move over. These are all zeros. Doesn't make sense to try to do anything with them. All I got is going to read as what? Tell me. Minus 3v is equal to minus 6. Is that right? So the columns on which the pivots were sitting, so these were the pivots originally. The first non-zero entry of each row, we call them pivot. Anybody who was in the column of the pivots is going to stay put. Other guys are going to move to the right. Well, this is a coefficient of y. We are writing back in the traditional notation. So this is minus 2y. Going to the right makes it plus 2y. This was really 3u. Moving to the right is minus 3u. Here, 2 and 3 are going to stay put. This is 2z minus 3v. They stay put. 5u, I moved it to the right. If you wish, you can write it underneath that to make it look nicer. This was minus 3v. This is a pivot, stays, and the numbers on the right hand side stay anyway. Okay, now after all this work, what have we achieved now? What was so big deal about doing all this? The left hand side of this thing looks like what? Triangular form, just like stuff we had done before. So this is the big deal about what we did, is that this is exactly like a triangular form we are used to. A triangular form like this. This was 5z equal to minus 10, or minus 3y plus 2z equal to 17, and so on. Triangular form. Here we have our triangle. These things were just neatly zero. After you have done echelon, and after you have separated the free from dependent variables, and after you have moved the dependent variables, after you have moved the free variables to the right hand side, what you have is triangular form. What do you think we are going to do next? Well, what did we do with the triangular form here anyway? We have just applied the back substitution. You do the same thing here, except your stuff on the right hand side are more crowded. They have these parameters in them, or these free variables. You have to live with them. So last one, straightforward. From the last one, what do I get? So this one is not that bad. Just v is equal to 2. Is that right? Minus 6 over minus 3, that makes me v equal to 2. What do I do next, you think? I just go back up. I do the back substitution. Let me write it here. So I'll have 2z minus 3v. v was 2, so it's minus 6 is equal to 2 minus 5u. So that tells me 2z is equal to 8 minus 5u. So that tells me z is what? Say it again. 4. We divide by 2, is that right? So z is equal to 8 over 2 minus 5 over 2 of u. We divide everybody by 2. Clean up as much as I can. Is everything clear so far? What do you think I am going to do next? So I got that. I got this. What is left? What is left is that we will need to go get the x. So we just get okay. So we come and say this equation. We have 3x. What do I put instead of z? I have 1z. This is just 4 minus 5 halves of u. That's my z. And what do I do for v? That's just 2. So this one came out of here, and this one came out of here. And right hand side I still have 14 plus 2y minus 3u. Now we have to have our eye on the prize. It's just, this is alphabet soup, all sorts of things thrown around at us. What is it that we want? We want x. We are gonna, this is rather arbitrary designation, but we are kind of treating x, z, v slightly differently than we treat the rest of them. It all depends how you wrote your equation from the start that distinguishes one set of variables from the other one. So here, from all of this, we try to find x in terms of others, which simply means everything else got to move to the right. So help me out to do that. Yeah, I don't want to go to the next page. 3x. So 4 and 2 is a 6. I move it to the right. Oh, what's going to be left then? 8. Very good. And then all that is left, I have a 2y still. I have 2y. Minus 3u. Maybe I write that minus 3u. Minus 5 halves go to the right and becomes what? Plus 5 halves of u. I need to clean up a tad bit. 8 plus 2y. And what's going to become out of that? Negative 1 half of u. So minus 3 plus 5 halves makes negative half. So finally, what is x? Yeah, we are just going to divide everybody by 3. So that becomes our x. Now, since we are out of time, let me so in the next class, what we are going to do, we are going to start with a problem that this portion hasn't been done. So as comparison goes, this is an easy problem. This is much of it has been done, and we just move things around. In the next example, there will be a matrix that is filled in with numbers, and much of the effort is going to go into getting rid of them. And we are going to practice Gaussian elimination and the standard ways of doing it. And at the very end, the solution that we are going to get is going to look like just what we had here. So at the end of this problem, x, z, v are going to be listed next to each other. So the final stage of this problem has to be listed as these are your solutions. Okay? So I'll see you on Friday, and we are going to talk about this thing a little bit more. Good luck. and God bless.